Any question?
That's also kind of.
You are welcome back to FANOG monthly meeting. Please, if you have your question, you can ask now. This is now the time for questions. So if you have any question relating to Dr. Lateef's presentation, you can now ask. You just unmute yourself and then you ask. Yeah. Anybody with any question? So if you have any question, you just unmute yourself and now, yeah, and ask your question. If we don't have question, I think
I think probably others are still joining.
yeah,
Can wait some
okay.
time.
Okay,
People are still joining.
yeah, correct. Let's give some time to see, especially the person that
Maybe what I can also do is let me share some of these slides because I know I was kind of very fast
okay.
the other time trying to manage the time. So I could perhaps just share some key points that I couldn't make.
Okay,
I was just fast about
let me
trying to
permit
wait
you
for
to
people to
share this
join.
slide. Yeah.
So
You can share your slide now.
oh, my boss is here, so I have to also take note of him. He was my BSc supervisor and was the
Okay.
supervisor of my supervisor for both
Okay.
PhD and MSc.
Okay.
Professor Oguntuashi.
Uh,
He supervised my first degree and has always been my boss up to
uh,
this moment.
Prof. Guntu Ashe, we are glad you joined us, sir. Prof. Guntu Ashe has been a mentor of mathematics, the mathematics community in Nigeria for so many years. He's still very, very active and is currently the editor-in-chief of the Journal of the Nigerian Mathematical Society. So it's a privilege having Prof. Oguntu Ashe to join us in our meeting. Prof, we are sending our greetings to you. And our presenter today was your mentee. That's Dr. Jolaoso. Is really glad for your mentorship over the years. We are glad, sir. Thank you, sir.
Thank you, sir.
Yes, sir.
So have you given me the opportunity to share my
Yeah, you
slides
can
so I
share
can
your slide
just
now.
have some of the points I was very fast about the other time.
Okay. You can share your slide now.
Okay. Okay, and maybe I can start from the image processing. I know I was kind of very fast the other time. How did
Yeah.
we formulated the image processing problem as an optimization problem and then proceed on to implement our algorithm in terms of reconstructing a blurred image
Okay.
by removing some noise from the blurred image. So first and foremost, the other point I mentioned about this year, sorry. So we have this the image processing problem itself is this problem we have a call inverse problem. Because this is the true image, we are the original image, or we call it the true image that we want to reconstruct. However, what we have is the true image passing through a block process together with some noise. So we have this corrupted image from the system. So in normal image processing formulation, the essence is to see if we could find X from this inequality, taking note that from this equation we have here, taking note that this H here can be of any types of, it can have any behavior. Most importantly, you have to find the inverse of H. So if H is a very large matrix, getting the inverse may be very, very expensive. So in order to do that, to find X, author comes up with this also. I have not. So they come up with this, that solving this minimization problem is the same thing as finding x, because you are minimizing this function with respect to x. So they come up that we could solve for x by minimizing this function, looking at the behavior. So that's what the engineering people do. But after what they just does with after this reformulation problem, they put in their tools and do other stuff there. But to the mathematics, we go into to look at the behavior of this function. I know that this particular function here is differentiable. This other part is not differentiable. How can I solve this? So there are tools for that, but the tools they are using, basically image processing, are tools that have been available for a very long time. So that's why we have to keep developing new algorithms that perform better than the existing ones in the literature. And that's where the algorithm we have built come into play, because what we did was we studied the behavior of these two functions together as a whole, as an optimization problem, considering this as a convex and smooth function, why this is convex and not smooth function. And with that, I know I can either solve this problem directly using the composite optimization problem, or I solve this via the monotone inclusion problem by considering the first order optimality condition of this problem itself. And also, I can also solve this problem by the variational inequality problem. In other words, I construct a converse set that is constrained by this parameter I have here. So I have the converse set here, and then with this part as a monotone operator. So that's the three way I could use to solve this problem. But for the case of this paper, I used the monotone inclusion. I didn't use the other two. So what we did with the monotone inclusion is I know for the monotone inclusion, I can build an algorithm that for whatsoever behavior might be is a monotone operator, for whatsoever is maximally monotone, sorry, for whatsoever maximal monotone operator I've built, and where he is monotone, this function, this algorithm, I prove that it's going to be convergent based on some parameter. So in other words, once I'm able to reformulate this problem into a problem that has the structure of the monotone inclusion, then I will be able to apply the algorithm. So to do that, what I did was I pick those image, blur the process by using the exponential motion in MATLAB, and with that, I'm able to obtain this as a whole. So what is now remaining is how do I get x from this equation? And that's the essence of this problem here, which is being solved using my algorithm. So it's just a three-way process. I draw the process, I have this, I have this. I need to solve for x. I use this minimization, and to get that x using this minimization, I use my algorithm. And then eventually we have these images we have here. However, we can't read the performance of this image except we use some metrics, and that's where we have this SNR, ISNR, and the rest. So the full the details of the experiment was written in this paper. So this paper is available, I think, both in arXiv as well as in optimization, which is one of the top outlets for optimization problems in terms of publication. So both we could observe for the two images we tried, the pepper image and as well as the lighthouse image. So to the result part, the interesting thing is that though we're able to reduce the time for the lighthouse, but not for the pepper, but the fact that our algorithm give a better SNR value and ISNR value to for both images, it's far better. That result is far better, or it's something interesting to the community compared to other results. These are reflective forward backward method and the rest of the other forward backward method we tried. And to also point that for the machine, for those in the engineering, most of the results they use either ADMM or the classical proximal gradient method. Because they basically depend on the tools that has been developed for a very long time, which was developed based on classical proximal gradient algorithm. So our whole case, we are not coming in by developing other method outside the classical proximal gradient method in existence and see if we could give a new algorithm that will do exactly the same thing that was done by the classical gradient method. So that was the case of the image process. I couldn't explain this in detail because I was kind of just very fast to see that I managed the time the other time. As well, we can also make a brief discussion on the machine learning experiments as well. So it's just a similar problem with what we have in the image processing, except that in this case, we're dealing with machine learning. So some data set comes into play. So in this case, these data sets are available, they are open source. You could find them either from Google or from UCI. So there are several of them. I could remember in the experiment, I used to this set. One is a banknote, the other focuses on I think it's a spam. Yeah, was it a spam email? I can't remember. I know I used two data set for the experiment in this paper itself. So but the key thing, the difference between the two data set was one was balanced, the other was imbalanced. So I have to perform some engineering to balance the data sets. So let's just give a brief explanation of how this comes into play into optimization. So we have the problem we want to solve. This is the logistic regression problem. We try to predict if, based on some features that has been extracted from the image, or if it's going to be an authentic banknote or a counterfeit banknote. So that's the essence of this logistic regression, or both one with regularizer. So in the experiment, I use this with regularizer. So I understand that this function here is convex and smooth, while this part is non-smooth, meaning that I can use my proximal gradient, or I can solve this via the composite optimization, or via the motor inclusion, or the variational inequality. So, but for the case of this paper here, we use the inclusion problem as well. We solve this using no difference of convex function. So I solve this using the small composite function, where I have two convex function, means I take the difference in this case, because the essence of that is I treat this part as a negative part. So by putting double minus here, so I could use difference of two function, reformulate this. The details of this experiment is given in this paper. It's open access, and you can always find it by just searching. I will plead with Dr. KK if you could make this slide available so people could check some of these things later on, if those who are interested in this aspect of work. So so what we did was we treat this part being convex and smooth, this part convex, not smooth. We treat them, we could deal with this part with the proximal operator, and this one we could take the derivative, implement it in our algorithm. Let's show the algorithm. Yeah, we have our algorithm here. So I use this for the case of the algorithm. My initial starting point here, I'll point the width of the data set that is being read into the machine. So I did that. We have the data set, the features, pass through, do some pre-processing to clean up the data set from missing value. And I think for this particular case, we don't have any missing value. I reported it somewhere that there is no missing value. So it means the data set is being cleaned already. So you just have lesser work to do. We implement it for experiment directly like that. So and the essence of the performance metric is just to measure the performance of the algorithm. How is it being able to predict from the testing data set if its performance using the testing data set rather than the after training with the set. That's why we have some splitting here. So we are training with some sets of data sets, keeping some aside for testing. So after training with this, we check the behavior, the performance of the algorithm by the metrics using the testing data set. And that's what we reported here, looking at the mean absolute error, mean square error, and then the root mean square error. So our aim is to see that this is reduced as much as possible. Though for our experiment, in the first experiment, we couldn't reduce the errors as much as we like. But for the second experiment, we could do that. So that was why the paper was being sent out for publication, because we be able to achieve a new result using our algorithm rather than using the popular ADMM, which many authors of the engineering are using basically for their experiment. So that was the key thing, the interesting thing about this aspect of application. So our aim is to develop algorithms that will perform better than the existing ones we have in the literature or the classical one that basically is being used by others. So we are still working on this. There are still many other algorithms we are developing, trying to see if we'll get good results thereabout. So probably, I don't know, maybe we could take the questions now.
Thank you. Thank you, Dr. Jolaoso. In fact, we are really glad, and you've taken your time to go through especially the last part of your presentation. So we want to find out if you have any question, please do that so that we can round up. It's a long day already. So if you have any question, you can unmute yourself and then you ask your question. In the next 5 minutes or thereabout, we should round up. So if you have any question, you kindly unmute yourself and then you ask.
Hello. Hello.
Yes.
Hello, Dr. Lateef. Thank you so much for your presentation. I don't have much question, only that the area I want more explanation is on the part of, you talked about gradient algorithm. You explained much about it, but I want to know if you can throw more light on. Hello? I don't know if you get
Yeah,
my
we
Yeah,
can
no, I
hear
can
you.
hear
We
you.
can hear you. Go
You
ahead.
say is the extra ingredients
Yeah.
algorithm.
Yes, and you can just to highlight some of the important and the way we can actually work on that.
Okay. Let me just throw the extra ingredients algorithm. Okay. Can I share my screen, please?
Yeah, you can. Go ahead.
Okay, yeah. So I think this is the classical extra ingredients algorithm that was proposed by Popov. So when it comes to optimization problem, the essence of in terms of development of algorithm, one of the key things we're interested about is looking at what is the convergence rate of your algorithm? How is it performing better? What kind of method have you developed for selecting the step size? There has been several results on this, still ongoing. I think currently people are, for example, introducing the kind of different types of inertial techniques to the algorithm. And as well as trying to see if they could reduce the number of projections they have in the algorithm. Though I'm kind of very skeptical about this. I think with my recent discussion with several authors, like, yeah, we've had a lot of algorithms with inertia that now it's even kind of being irritating with inertia. So journals are very selective now when it comes to publication with inertia because it's more or less like just redesigning what other people have done. So I advise people to see if probably they could look into or study the rate of convergence because there haven't been much work on that aspect. So instead of just adding inertia or modifying one algorithm to another thing you could do as well is that, yeah, you have the inertia. For example, you know that a classical algorithm converge at the rate of the big O to the inverse of K. So, but it will be interesting, which is a linear. If we could have more than maybe the sublinear rates, perhaps, of the algorithm, you can study into that, as well as aside that, you can also see if probably there's a way you could design an algorithm that uses lesser number of projection apart from the existing one, or perhaps the rate of the method of proof as well. If you could relax some of the conditions being used currently, most of the either you assume that operator T is monotone, pseudo monotone, or quasi monotone. So there are still that like I explained earlier on, this monotonicity all surrounded by they are surrounded by convexity. Not much work has been done in terms of non-convex aspects. You could look into the non-convex optimization by considering variational inequality where the operator T is non-convex. In other words, the idea of monotonicity will not be satisfied because, I mean, like I said, monotonicity is more or less like just talking about convexity. Ideas in this area of research. Though people are publishing, but most big journals now are very skeptical about works on variational inequality, most especially when you are just adding inertial term to it, without really making much impact on in terms of novelty you have added to the research. I don't know if that answered the question.
Yes, except the fact that you've not been able to also comment on subgradients. So I want to know more about subgradients problem.
Oh, you mean the different? No, for the case of the subgradient, it's just reducing the projection from 2 to 1. So instead of having PC at the second layer, at the second step here, then you rather have a projection to onto an half space. So remember, this C is a convex set. It's just like the general a subset of the entire space. So what other that was introduced by, I think is it Reich also in the 2001, where introduced that instead of projecting the second step into C, you project into an half space that is constructed by using the steps from YK. Is that what you want to understand?
Yes, yes, yes. Thank you so much.
Yeah.
Thank you so much, sir.
Thank you very much, Dr. Lateef, for that question. I don't know if we have, Olawale is raising up his hands. You can ask. Ask your question, Olawale. You can ask your question. Unmute yourself.
Thank you for the organizers of this seminar. Well, I really don't have a question. Just to thank Dr. Jolaoso Lateef for a well-explained talk. We really appreciate and we've enjoyed everything that he has presented. Thank you. Thank you very much.
Thank
We
you.
had that the person's colleague, we lived together during my postgraduate, so he's a well-known friend of mine. So
Wow. Yeah, welcome, Wale. We are glad that you are with us. I want to take one or two questions before we go. If you have just one or two, and then we are done. It's a long day already. So, anybody with any question? I think that should be the last question before we go. Otherwise, I think we are done. Any question?
Good morning, everyone.
Yeah, thank you.
Hello.
Yeah, Dr. Peters,
hello.
thank you for joining us. We are listening. Dr. Jolaoso is listening.
Okay, my apologies. I've been trying to join the meeting, but due to network problems, so I joined very late. But I think I've been able to connect to the seminar.
Yes, we are going to share
So I
the
just
Dr. Jolaoso's slide. We are going to share it in all our platforms, Nigerian Mathematical Society and all other platforms. So we're going to get the access to the materials.
okay. That's good. I will appreciate that so that we can listen and read it also more in detail.
Yes.
So I just want to thank him for the wonderful presentation. And then I don't have much question because I didn't follow in detail, but I know he was talking about gradient methods. And I know the interest is to, one of them is to reduce the number of projections, because if the convex set C is not as we wanted, projection can be difficult to compute. So, but between this thing, the subgradient, and then also the Sang method, the worry also is in the operator, because the Sang method, we might need to have a better operator, because you need to compute the operator in two places. So my question to the presenter is, the two methods, like which one do you think is more recommendable? Because the other one avoided projection, but also you have to compute the projection twice. Sorry, the operator twice.
Okay. Let me share my slide to explain about that.
Hello?
Can you see my screen, please?
My question.
Yes, we can
your
see
slide.
it. We can see it.
Okay. About this T-Seng, the fall backward forward is
Okay,
also
yes, I
as
can
the
see it.
T-Seng
Yes.
extra gradient method. For the case of note for variational inequality, why I will just explain this with aspects of the either the subgradient extra gradient or the gradient extra gradient method. For the case of the fall backward, though we have two evaluations of the function, as we could see B here, is being evaluated at 2 points, sk and yk. The same thing for the both subgradient, extra gradient, and extra gradient method. Let me just pick an example of that, I think. Yeah, this is the extra gradient method, where you have both evaluation of T of sk, then at 1 point, and then you need this at another point. But to point out here, it takes more evaluation. Like, for example, when your C is not well behaved, how do you deal with it? Like you just mentioned, for the case of the projection to C. Though you are reducing when you are moving from, for example, extra gradients to the backward forward. However, the cost, if the cost is there because it's not for free, yeah, it has to come at the cost of evaluating the point, the function at another point. And to answer that, the best method so far in terms of computation is still the pop-off, because for the case of pop-off, you have only one evaluation of the operator at 1 point, as well as one projection of the operator. So it's still kind of being balanced compared to the other method in terms of numerical computation. So when you run your experiment, it all depends on the kind of experiments you are dealing with. For some, you always have the T-Seng method performing better than the subgradient extra gradient. Though in most cases you have that, but in some cases you find some example whereby your subgradient extra gradient performs better than the T-Seng. So it depends on which kind of experiment you are considering as well. So all these things are still susceptible to experiments, like I said earlier on. So in other words, just to wrap up, extra gradients, subgradients, T-Seng, apart from the extra gradient that has two projections, the T-Seng has two projections, one projection and two evaluation of the cost operator. But the pop-off has one projection. I think I didn't put the pop-off here. So the pop-off has one projection and then one evaluation of the cost operator at a particular point. And if that answers the question.
Thank you, Dr. Jolaoso. I think you've done justice to all the questions, and we are really grateful. We are going to share the slides in all our various platforms. We've also recorded the lecture. So both the video and the slide will be shared so that we can make reference to those materials. So we want to thank you, Dr. Jolaoso, for being our guest speaker for this month's seminar. We are glad for your experience and your willingness to mentor, especially our postgraduate students, as well as other researchers. So we are really grateful, and we want to plead that next time we call on you, that you also respond the way you did this time. So Dr. Jalaosho,
Thank you very much, Doc. I really appreciate it. And as well as thanks everyone for attending the talk, most especially my lecturers and from the Federal University of Agriculture, Abeokuta, Professor Oguntuashi and Professor Osinoga. I appreciate your presence here as well. And also for imparting the knowledge on us during the time we spent at the university. So I am also grateful. It's my pleasure to be here, and I will always respond to the call from Nigeria. Nigeria is still my home country, no matter where I've been to.
Thank you very much. And to all our participants, I want to thank you. Very soon you will hear from FANOG regarding our next month seminar. So we want to appreciate everyone for joining us. We want to end the lecture now. So thank you, everyone.
Thank you. Bye-bye.
Yes.